These are the notes for AP Calculus on the topic of extreme values, looking at increasing, decreasing intervals for position, velocity, acceleration, and speed. So this is a particle travels along the x-axis according to the position function. Notice here they're calling it x of t to remind you it's moving on the x-axis, and they use the interval 0 to 3 where t is in terms of seconds. So let's go ahead and draw. Here's our x-axis here. So this particle is moving along this x-axis. And in part A, we're asked that t equals 3, is the particle traveling to the left or to the right? Well, if the particle is traveling this way, to the left on the x-axis, that must mean the velocity, if that's going in the negative x direction, the velocity must be negative or less than 0. Whereas if the particle is traveling to the right, that would be because the velocity is positive. In other words, it's greater than 0, because that's the positive x direction. And that's how we're going to end up justifying our answer. So remember, when you have the position function, the velocity function, in this case v of t, is just the derivative, first derivative of the position function. So it could also be written as x prime of t. Would be, just use the power rule here, 3t squared minus 10t plus 8. And that's our velocity function. That tells you the velocity or instantaneous velocity at any specific time. And in this case, we want it specifically at time 3. So you just substitute in 3 there. So v of 3 would equal 3 times 3 squared minus 10 times 3 plus 8. Well, that gives you 9 times 3, 27, minus 3 times 10, 30, plus 8 gives you, that's 8 plus 27, 35, minus 30, that's 5. And the units here, since moving on the x-axis would just be units per, sometimes they don't give you the units per time, but here they tell you times in seconds, so it'd be units per second. And since the key is that since that's positive, we know the particle is traveling to the right. So we can turn this question into a statement and say, at t equals 3, the particle is traveling to the right and then to justify it, simplest way to do that would be since the reason why we do is traveling to the right was because our velocity at time 3, which you could write as v of 3, is you could write it as positive, or a simple way to write it is greater than 0. Now, with the same position function here, part B and C are related. Part B says when is the particle furthest to the right, on the x-axis in other words, and part C says when is the particle furthest to the left, and then what is its position at those times. So furthest to the right on the x-axis, that's another way of saying you're trying to find the maximum or absolute maximum position. Similarly, furthest to the left, that's the minimum position, or absolute minimum position. Okay, so the key thing to remember, whenever you're trying to maximize or minimize, you need its derivative. In this case, the derivative position is velocity. And that's, if we want the minimum maximum position, we're going to set the derivative position, x prime of t, which is the same as velocity, equal to 0. So we already got that in the previous part. Velocity was 3t squared minus 10t plus 8. So let's set that equal to 0. And to solve that, we would factor. So we look for factors of 24. The sum is negative 10. And what would work there would be negative 6 and negative 4. Multiply to be positive 24, add it to be negative 10. And we can use those two to split up the middle term. So we have 3t squared minus 6t minus 4t plus 8 equals 0. And then you split in half and group factor it. The factors of the GCF in the first two terms is 3t. And that leaves you with t minus 2. The GCF of the second two terms is negative 4. That leaves you with t minus 2. Then they have a GCF. They both have t minus 2, so you can factor that out as a GCF. And the other factor left would be 3t minus 4. So in order to be 0, one of these has to be 0. So if you set t minus 2 equal to 0, you get t equals 2. If you set 3t minus 4 equal to 0, you'd add the 4 divided by 3 to get t equals 4/3. So those are our two critical numbers. And let's double check though. Are those in the interval 0 to 3? 2 is, and 4/3 is also, that's like 1 1/3. So they both are. If either of them were not in the interval, they'd be irrelevant to the problem and we would cross them off. In this case, they both are. So let's go ahead and draw our number line now, and then test, see what's happening. And we're just looking from 0 to 3. And we're testing this in our velocity function. And this is just our factored form of velocity. So we put 2 and 4/3 on there in order. So we get 4/3 first, and 2. Both of those make the velocity 0. And then we just need a test in between there to see if it's positive or negative. So velocity here, if we test 0, that's not a correct number. 0 makes this factor 0 minus 2 is negative. 3 times 0 is 0 minus 4 negative, and negative times a negative will be positive. Between 4/3 and 2, that's kind of a tough one. 4/3, but 2 is the same as 6/3, so you could test 5/3. You want to test between them. 5/3 minus 2, well 5/3 is a little bit less than 2, so that would be negative. And then when you test 5/3 here, notice what will happen is, for t to the 3's will reduce that, you get 5 minus 4, which is positive. So you have a negative times a positive is negative. And then over here you can test 3 because it's not a critical number. 3 minus 2 is positive, 3 times 3 is 9, minus 4, that's positive. Positive times positive is positive. So what this shows us, in terms of the position function, is the derivative of position. So that means position must be increasing when velocity is positive, decreasing when the velocity is negative, and increasing. Or another way of looking at it is moving to the right, moving to the left, and moving back to the right. So we sketch a little graph of what this could look like. It's increasing, decreasing, increasing. And that allows us to see, well, for our absolute maximum, when it's furthest to the right, there's a couple possibilities. It could be at 4/3, one possibility, or it could be at the endpoint 3. It could be a relative max 4/3 or an endpoint 3. And then to compare which one it's at, we would just go back to the position function to see which one's larger. So for the absolute max, we're still on part B, and we're kind of doing some of the work for part C as well. But we'll start off with part B. The absolute maximum, we'll test x of 4/3 versus x of 3, and see which one of those two is larger in this case. So we'll put a maximum. So we'll go back to our position function. So this would be 4/3 cubed minus 5 times 4/3 squared plus 8 times 4/3 plus 1. Well, 4 cubed is 64 over 3 cubed is 27. Okay. And then if we square this out, this would be 16 ninths. Right? And then times 5, that would be 80 ninths. But we want to get a common number or to add these together, so if you multiply that by 3 over 3, that would be the same as 240 over 27. So our common number would be 27. And we multiply these two, 8 times 4/3, that's 32/3. But again, let's get a common number of 27. Multiply the number by 9. 9 times 30 is 270. 9 times 2 is 18. 270 and 18 gives you 288. Oops, this was a negative term. Sorry about that. So there's a minus there. And then this one's positive, and that was 288 over 27. And then 1 is the easiest one to get a common number, just multiply by 27 over 27. 1 is the same as 27 over 27. And let's combine those, let's see what we get. So let's take the 288 minus 240, that's 48. 48 plus 64 is 112. 112 plus 27 is 139 over 27. So that's the y value, 4/3. And now let's compare that with 3. So if we substitute in 3 in the position function, 3 cubed minus 5 times 3 squared plus 8 times 3 plus 1. So this will give us, let's see, 3 cubed is 27. 3 squared is 9 times negative 5, negative 45. 8 times 3, 24. And then plus 1. So let's combine the positive numbers first. 21 plus 4 is 25. Plus 27 is 52 minus 47. 45 is 7. So what's larger of those two? Well, does 27 go into 139 7 times? No, it doesn't. So 7 is larger than 139 over 27. So we can say answer the two questions there. When is the particle furthest to the right? The time is at 3, and what is its position then? Its position is 7. So you can say either one first. You can say the particle is furthest to the right at t equals 3. And then what is its position? When its position is 7. Well, t equals 3 in the units per time every seconds. And you can put 7 units, I guess. Okay. So that answers part B of this question. Now let's look back at our number line and we're trying to find the minimum position. So we can take a look and see the places where the minimum could potentially occur. Is at the relative minimum here at t equals 2 or at our endpoint of 0. So to figure out the absolute minimum, let's compare those two again back in the position function. So we'll compare x of 0 to x of 2. Well, x of 0, that just wipes out everything except for the 1. That's just 1. And let's compare that with x of 2, so that would be 2 cubed minus 5 times 2 squared plus 8 times 2 plus 1. So 2 cubed gives you 8. 2 squared is 4 times negative 5, negative 20. 8 times 2 is 16 plus 1. So let's see, it's the positive numbers first. 8 and 16 is 24 plus 1, 25 minus 20 is 5. So here we're looking for the minimum, which you can see it would be 1 of the order of the 2. So we can say the particle is furthest to the left at t equals 0 seconds. When position is 1 unit. So notice our absolute maximum position occurred at time 3 at an endpoint, and absolute minimum occurred at time 0, also at an endpoint in this case. So sometimes they occur in our relative as a maximum, but not in this particular problem. Okay, now let's take a look at some more parts of this question. So it says for D and E, these go together. At what time does this particle reach its minimum velocity? And what is the minimum velocity? And part E, at what time does the particle reach its maximum velocity? And what is the maximum velocity? So the key concept to remember here is whatever you're trying to minimize or maximize, you need to use its derivative. Notice when we were trying to minimize and maximize position, we used the derivative position, which was velocity. So if we want to minimize or maximize velocity, we're going to set the derivative velocity, which is acceleration, equal to 0. So I don't think we have our acceleration function yet. So a of t, which is the same as the first derivative velocity, and velocity is the derivative position, so that's the same as the second derivative position. We look back at our velocity function right here. Oh yeah, 3t squared minus 10t plus 8. If we take the derivative of that, that would be 16 minus 10. So that is our acceleration, and that's what we set equal to 0. And to solve for t, you could add the t over and divide by 6, or I could just factor out 2, be left with 3t minus 5. Either way, you can see that if you set this equal to 0, t would equal 2 isn't 0, so if you set this one equal to 0, you get 5/3. You add the 5 and divide by 3. Now let's check, is 5/3 in our interval between 0 and 3? Yeah, 5/3 is 1 2/3, so it is. So it is relevant to this problem. So let's draw our number line in. And again, the endpoints of the interval we're given were from 0 to 3. And now we're looking at acceleration a of t. And 5/3 is the only value that makes that acceleration equal to 0. So here we could test 0, because not good, remember 0 minus 5 would be negative. And here we could test 5/3 is 1 2/3, so you can test 2 or 3. 3 times 2 is 6 minus 5, that's positive. So the acceleration, now this does tell us, this is the second order velocity, it does tell us something about the position function as well. But what we're interested in is what it tells us about the velocity function, v of t. What it tells us about v of t, so it's just like the velocity was the derivative of position, it told us where position was increasing or decreasing. In the same way, acceleration is the derivative of velocity, so it tells us where velocity is increasing or decreasing. That's the slope of velocity. So if acceleration is negative, that means velocity is decreasing. And if acceleration is positive, that means velocity is increasing. So if we sketch a little graph of this one, decreasing and increasing, what's the minimum velocity and what time does it reach that? Well, in this case, you can see the minimum velocity has to be at 5/3. There's no other place it can be. So you can just say, you just need to know what the minimum velocity is, so just plug it back in the velocity function. Plug back in 5/3. So remember our velocity function was 3t squared minus 10t plus 8. So it'd be 3 times 5/3 squared minus 10 times 5/3 plus 8. So if we work that out, squaring that out, that's going to be 25 over 9. But times 3 reduces that to 25/3. Minus, that's 50/3. And 8 is the same as 24/3. Add those together, that's 25 and 24 gives you 49/3, minus 50/3 is negative 1/3. So that's the actual minimum velocity. There's different ways to word it. Probably the most compact way to word it, since again you want to know what time does it reach the minimum velocity and what is the minimum velocity, you can say the minimum velocity is or equals negative 1/3, and the units would be units per second. At the time it occurs at is t equals 5/3 seconds. So that answers part D, and we have most of the information we need to figure out part E as well. So if we look back at what the graph of velocity looks like, decreasing, increasing, you can see the maximum velocity could occur at a couple different points. It could occur at time 0, that endpoint, or at time 3, that endpoint. So we have to compare those two to see which one's larger. So let's compare v of 0 with v of 3. Well, v of 0 would wipe out everything in our velocity function except for the 8. And v of 3 would be 3 times 3 squared minus 10 times 3 plus 8. Let's compare which of those is larger. So 3 squared, 9 times 3 is 27. Negative 10 times 3, negative 30. Plus 8. That's 35 minus 30, that's 5. And you can see the maximum would then be 8 at time 0. So let's say the maximum velocity is 8, and the units will be units per second at t equals 0 seconds. All right, let's go on to the next part now. Now, for parts F and G, it says is what time does the particle reach its maximum acceleration, and what is the maximum acceleration, and what time does the particle reach its minimum acceleration, and what's the minimum acceleration. So again, following that same concept, remember whatever you want to maximize or minimize, you need to take its derivative. When we wanted to maximize and minimize position, we used its derivative velocity, set that equal to 0. We want to maximize and minimize velocity, we use its derivative of acceleration and set that equal to 0. So if you want to minimize or maximize acceleration, what we have to use is its derivative, a prime of t, and set that equal to 0. Purple numbers. So let's look back at our acceleration function, which was 6t minus 10. So the derivative of that, well, that would just be 6. So when you try to set that equal to 0, well, that's never 0, that's just 6. So that actually makes it even simpler, because when you draw your number line now, that means there's no critical numbers because the derivative of acceleration is never 0. And we put your endpoints on there. Zero and 3. Notice you can test anything here, and we're just going to get positive 6. So our derivative of acceleration is just positive the whole way, this whole interval. And if the derivative of acceleration is positive, that's the slope of acceleration. That tells us an acceleration function, a of t, would be increasing the whole way. You can see that makes sense because acceleration, if you look at it, 6t minus 10, that's just a linear function. So here, the maximum acceleration, you can tell it's got to be at 3. The only question is, what is that acceleration? So just plug it in our acceleration function, a of 3. And our acceleration function was 6t minus 10. So it'd be 6 times 3 minus 10. That's 18 minus 10 is 8. So I can say the maximum acceleration is 8, and the units for acceleration will be units per second squared, and that occurs at t equals 3 seconds. That answers part F. And then part G, for the minimum acceleration, well, we can look back at our sketch of our graph of acceleration, we can see the minimum would have to be at 0. So we just have to find out what that is. So a of 0 will be 6 times 0 minus 10, so you just get negative 10. So there's our minimum acceleration. Let's say the minimum acceleration is negative 10. The velocity was units per second. This would be units per second, which is units per second squared. At t equals Finally, let's talk about speed. Remember how speed is defined. It's similar to velocity. Sometimes the words are used interchangeably, but they don't quite mean the same thing. Because velocity can be positive or negative because it indicates direction, whereas speed, remember, can never be negative. It's the absolute value of velocity. It just indicates how fast something is going, regardless of direction. So, oftentimes you may be asked, is the speed of something increasing or decreasing? In this case, it says at time 1, for the same problem, is the speed of the particle increasing or decreasing? So, in other words, is it getting faster or slower? So, what we have to look at here are both velocity and acceleration. So, velocity and acceleration are the same sign if they're both positive or they're both negative at a specific time. That means speed is increasing, because then velocity and acceleration are working in the same direction. They're both making it more positive or more negative. However, if velocity and acceleration are opposite signs, if one is positive, one is negative, then the speed is decreasing. Then acceleration and velocity are working against each other. So, whenever you're asked if the speed of something is increasing or decreasing, you need to know both the sign of its velocity and the sign of its acceleration, so you can compare those two. So, we've already got our functions from the previous parts here, so we just need to know specifically at time 1, what's the sign of the velocity, v of 1, and what's the sign of the acceleration, a of 1. Alright, so v of 1, our velocity function, remember, was 3t squared minus 10t plus 8. 3, 1 squared, minus 10 times 1 plus 8. That's 1 squared is 1 times 3, that's 3. 1 times negative 10, plus 8 gives you positive 1. So, our velocity is positive. That means it's moving to the right. And acceleration, function, remember, was 6t minus 10. So we do 6 times 1 minus 10. So that's 6 minus 10 gives you negative 4. So that's negative. So that means it's moving right, but the acceleration is negative, so it's making it less positive. So it's working against it. So that would mean speed is decreasing because they're opposite signs. So we can say at t equals 1, the speed of the particle is decreasing. And to justify that, all you have to say is since, let's talk about both position and velocity, v of 1 is greater than 0 and acceleration of 1 is less than 0. And that concludes the notes for AP Calculus on the topics of extreme values and increasing and decreasing intervals related to position, velocity, acceleration, and speed.